All right. Good afternoon again to everyone. Welcome to the first webinar, which is jointly organized by the Special Interest Group of Challenges of the MICCAI Society and also the MICCAI Student Board. I'm Lena Meyer-Hein from the German Research Cancer Center, and I welcome you actually on behalf of the entire Special Interest Group of Challenges. So who are we actually? 4 years ago, the MICCAI Society actually launched a working group for challenges, where the mission was to raise MICCAI challenges to the next level of quality. And last year it was then decided to convert this working group into a special satellite organization in the MICCAI Society. This is called the Special Interest Group, SIG. The former working group now forms the board of this organization, but we're also making sure that the members, that we have members that represent organizations that go beyond the MICCAI Society, because we really want to make this a worldwide effort. We're in our starting phase now to form the group, to form our vision, to start the activities. But one of the first things that we decided was to educate people. So this is why we started with this webinar. But before we go into the agenda, I would like to hand over to Annika, who's actually the secretary of the SIG, to update you on our current activities.
Yeah, thank you. Also, a warm welcome from me. This is just a very brief introduction of what we've been doing in the past and what we've been doing now and what we're aiming for. So this is a special interest group for challenges. So we're interested in enhancing the quality of challenges to assess the quality of AI algorithms, similar like we would do it with clinical trials for new medication. And challenges have a very high impact in our field, as you probably know, and this is probably the reason why you're joining. So the winners are new state-of-the-art methods, are highly cited, get high prize monies, but also challenges are very important for the research itself. So the mission of the SIG is related to science, but also practical issues. For example, we want to make sure that we have best practices regarding challenges, but we're also working on the infrastructure and want to help you guys by providing platforms for hosting and the evaluation of the challenges. We would like to aim for standardizing challenges and make sure that they are transparent. And we also like to support you in things like, for example, applying for funding. But we're also interested in education, community building. So we like to educate all of you for challenge organization, but also participation, validation, quality control, and all those things. But we also want to collaborate between different communities, and we're interested in incorporate feedback regarding challenges. So what we've been doing in the past? The first thing that we had a look at is the quality control of challenges, because there's a high discrepancy between the impact and the quality of challenges in the past. And we found that in previous years, there was a huge problem regarding the reporting of challenge results. So it was not really possible to interpret and reproduce challenge results. We found that rankings are quite unstable. And we also had a look at cheating, which naturally, unfortunately, happens in competitions. And we found that those issues lead to the fact that it's quite easy to cheat in challenges. And due to this reason, we also founded the previous MICCAI working group on challenges and now the special interest group. And we first introduced a submission system for the MICCAI challenge that was also used for other large conferences, in which people, so challenge organizers, had to insert structured information about the challenge in a very comprehensive way, so that it was easy to review the challenges and make sure that we only accept high quality challenges for those conferences. Based on this, we also worked on a reporting guideline for challenges with the bias statement for biomedical image analysis challenges. And this guideline concerns all the different parameters that are important to report a challenge, but also for designing a challenge, and really helps you to make sure that all of the necessary information is there. In the next step, we introduced the concept of challenge registration. So the whole challenge design is put online after acceptance with a DOI, where you can directly see all the information, even if it's not directly at the challenge website. And if there are some changes, which just happens for a challenge design. Sometimes you see, for example, that you should use a different metric or ranking scheme. Then the organizers report this to us, and those changes will be marked at the registration page. We've also been working on how you could analyze your challenge results. So, for example, we offer a toolkit that automatically analyzes your challenge rankings, for example, your results, for example, that you could do ranking uncertainty analysis, all those things that are really important if you analyze your challenge and want to make sure that these changes are also important. And sometimes you really see things that you haven't noticed before without an uncertainty analysis. Finally, our current project is on the validation metrics. So we have been working on limitations of metrics. So you find our paper on more than 50 images illustrating problems regarding metrics. And we're currently working on a problem-aware recommendation framework, where I would be really happy if you would like to give some feedback if you're interested in this topic. So you see the QR code, feel free to scan it and have a look at our survey. It could also be just a one-click feedback. And we're also working on initiating this whole framework for different biomedical use cases, as you see on the bottom. For example, for disease classification, dermoscopic images. This is, of course, something that is very important for challenges. So if you know a use case that you would like to have in the paper, feel free to reach out and fill out the survey and let us know which ones you would like to have present. And also, we will have a webinar series probably also on this topic. So if you're interested, there will be the opportunity to be educated in this topic. Yeah, we also have the opportunity for anonymous challenge feedback. So if you know a challenge where you saw some problems, or do you have some general feedback on MICCAI challenges, on other challenges in our domain, please feel free to fill this out. Just go to our SIG website and fill out this very short questionnaire. And we always discuss this in our SIG and make sure that we implement the changes. And we will also discuss different issues on Twitter soon. So if you're interested, stay tuned and have a look at what we're doing there, but also feel free to always drop feedback. Doesn't need to relate to a specific challenge. Yeah, and the next thing that we're working on and where you're currently in is the webinar series. We want to have specific webinars on topics related to challenges. And today we will learn on how we could win a challenge. And with this, I would like to hand over to Ping-Kun as the webinar host.
Thank you, Annika. Yeah, we are very excited about it. I know everybody is waiting to hear what our speakers will say, so I'll be very brief. Just talk quickly about the purpose of this webinar series. Through this webinar series, we hope to form and foster a challenge community within the MICCAI related areas. This webinar series will serve as a platform for our community members to share their experiences about the challenges and get help on challenge related issues. Not limited to the attendance and also organization review, etc. So the webinars will not only help prepare challenge organizers and encourage attendees, but also develop reviewers. We will announce the future webinars as it gets closer. So I would like the student board chair, Camila Gonzalez, to give a welcome and introduce our first speaker of the day. Thank you.
Thank you very much for that introduction, Ping-Kun. So I will very briefly introduce the MICCAI Student Board. So we are a student initiative that has existed since 2010, and we organize events during the MICCAI conference as well as throughout the years and advise the MICCAI board on matters of relevance to students. This is the current board. One important thing I would like to say is that we have our educational challenge going on, so we are accepting submissions for that until the end of July. If you have anything you would like to contribute, then please go ahead. Exactly, we also have a webinar series throughout the year and organize events during the MICCAI conference. These are just some of the events that we organized last year. Okay, and you can follow us, of course, in social media where we give regular updates of what we are working on. Here are our groups. And with that, I would like to introduce the first speaker of the day, Fabian Isensee, who you probably all know. So he has consistently enabled the translation of state-of-the-art algorithms to real use, most famously with the NNUnit framework, which I am sure a lot of you have used. This is the de facto standard for segmentation in the medical domain. And the methods that Fabian has developed have won numerous image segmentation challenges. So with that, I would like to give him the mic.
Thank you so much for the warm introduction. Let me share my screen, and please tell me if something is amiss, but I hope everybody should have enough, especially me, should have enough experience now with Zoom calls. So yeah, wow, it's really an amazing crowd. I see over 90 attendees here. That's overwhelming, and I really hope I can do it justice. So today, I'd like to talk to you about some challenge-winning strategies that I've applied over the years, and would really like to share how I'm approaching and thinking about competitions when I'm taking part. So to give you a little bit of a context, I just wanted to give you a quick rundown of the competitions I've participated in, and also show you a little bit the timeline of things how have been going. And really the first time I've been participating in competitions was in 2017, where we were really happy to participate in the ACDC challenge, where we could get the first rank, and then also the highly competitive breadth challenge. So that was really like a kickstarting moment in the whole segmentation projects I've been doing. And then over the years, there have been new challenges coming along. So many of you will be familiar with the medical segmentation decathlon, which was really the birthplace of NNUnit. So that one is really close to my heart. And in 2018, again, I attempted to win the breadth challenge. Unfortunately, a team from NVIDIA beat me to it. Notable in 2019 was the Kids Challenge, which was very competitive with over 100 teams. Finally, in 2020, I was able to get what I really wanted, brain tumor segmentation challenge win. And currently I'm working on the AMOS challenge. So this is really just to give you a perspective where I'm coming from, the things I've been doing in the past. And also I really wanted to highlight all the focus on segmentation here and these medical MICCAI related challenges, because that's really what my experience is, that what I can be talking about. So whatever I'm saying, please remember, this is my context, and this may or may not be applying to your context. So I'm really excited to hear the second talk of today, because James has won a really competitive challenge. And I must confess that none of these challenges here have been as competitive in terms of number of teams that participated. So these challenges at MICCAI typically run at 100 or less participants, with the largest ones being, of course, the well-known breast challenge and the kids challenge, which had a second iteration in 2021. But what I can tell you about, and this is, I think, something I could hopefully show with this slide, is that I was happy or lucky to consistently perform in challenges over many years, and I would like to share some of this experience with you. To give you a very rough outline of what I'd like to talk to you about, I'd like to talk to you about selecting challenges, understanding challenges, then general strategy, so validation environments, the research you do, what baselines you use, and how you use engineering and hyperparameter tuning to get things over the finish line. And I would like to acknowledge that I took some very loose inspiration from the blog post listed down here, simply to cross-check if I forgot anything. And really there were things that I added because I read it, so I would like to acknowledge it. Let's start with picking your battles. And to me, this is important. Not every challenge is worth fighting for. And the slide maybe also originates from a time where the special interest group wasn't as active as it is now, because challenge quality has been really improving over the recent years. And that's thanks to this group, thanks to Lena's team and many more, that this was possible. And it's amazing to see. But still, some challenges I would say are better than others. So what would you like to look for when you're browsing for challenges for next MICCAI? Maybe I really like it when there's the full description of data, when it clearly says what metric and what ranking is going to be used. It's even better if challenge organizers provide a reference implementation of everything, so that I can copy the exact setting at home. Does the validation make sense? Is it in line with what I would expect for this kind of problem? I always like to look at the annotation quality. I'm not going to participate in challenges that have visibly bad ground truth labels, because things are just too noisy and it's frustrating to compete. I look for anti-cheat measures because it's really annoying if you feel like people could cheat you for the win. So in this context, a hidden test set is like the bare minimum, but it's way better if people are asked to submit Docker containers or the like. And then, of course, what am I shopping for? What you're probably shopping for is what kind of fame, what kind of reward do you get when you win the challenge? So if there's a challenge with like a huge price tag on it, and for MICCAI challenges, for example, Kids 2019 was a really big one with $5,000 US cash prize, then that's, of course, something that also gets the motivation going. Also something Lena and Annika, especially Annika previously mentioned, and that's really important, is that the metrics kind of tell you what to do, right? If you're entering a challenge, what's a good segmentation? It always depends on the task. It depends on the specific application. And from that, the challenge organizers kind of derive metrics that kind of approximate their understanding of what a good segmentation is. And as a result, different segmentations or different outputs can be considered better or worse depending on what metric is being used. And I've tried to capture this in this really rudimentary example down here, where I'm just showing that segmentation 1, which has like a small outlier here, but a good overlap in the, so to say, main area, would be considered the better segmentation if the dice was used as a metric, and if the Hausdorff distance, which measures the distance of outliers to the ground truth object, was used as the primary metric, then segmentation 2 would be considered better. So this really just to highlight, it's important to understand what you're supposed to do and then do it so that the metric the organizers want to see is being optimized. And I would also highly recommend you to look into this publication here by Annika, because it really shows a lot of pitfalls and a lot of metric related things from which you can surely learn a lot. With the metrics, that brings me to a validation environment. And I think that's something many people don't do properly, including myself, because I'm lazy. But the proper way to do it really would, at the start of the challenge, either take the reference implementation from the organizers or copy it or build it as much as you can, as close as you can to the actual validation of the competition, because that's really, really important. If you don't do this, you will be optimizing for the wrong thing all along. And especially if you have, say, a team with multiple people and you're working together, build an internal leaderboard, compete against each other, because this competition is what's going to fuel your motivation and what's also making sure you're getting the best out of your time. And also it's really fun to kind of have jabs at your colleagues like, hey, my model is better today, but then they have to think of something new, etc. So it's a really cool environment to do it this way. Just to give you a visual highlight of why it's important to think about the metrics and of course also the ranking strategy that's being used by competitions, I would like to show you this figure, which I stole from Lena. So what you're seeing here is essentially a different number of algorithms that have been submitted to a challenge. And I think this is actually based on real world data. And then if you use different metrics or different aggregation schemes, so median aggregation, mean aggregation, aggregate then rank, rank then aggregate, etc., you see how the ranking can change a lot. And this can actually have an impact on the performance of your model in the challenge. And so it's really important to not just optimize for the right metrics, but also for the right ranking. And this should be part of your validation setup at home. So what I, for example, like to do is really implement exactly what the challenge does and then compete against myself or against my colleagues. To give you a little bit of a real world perspective on how metric and ranking ranking optimization can look like, I just give you a quick example from our Brett's 2020 submission. So the validation scheme here is that two metrics are really important, dice and 95th percentile of the Hausdorff distance. It's a rank then aggregate scheme, and the evaluation is based on regions rather than the raw labels. I will show you that in a second. So the first thing we do, of course, we want the dice, optimize the dice. So we do use the dice loss. That's a no-brainer. Everybody does this nowadays. The second thing is also something we did, but we didn't invent, but now it's something that's more or less standard in Brett's. So where you see Brett's has 3 foreground classes, the edema, the enhancing tumor, and the non-enhancing tumor. And these 3 foreground classes are not the ones that are actually being evaluated in the competition, but instead the competition evaluates on these regions. So what we do in the model is directly optimize these regions instead of the individual target labels. And finally, because of the way metric computation is implemented in breadths, and it has a good reason to be implemented this way, but it kind of rewards you when you remove small components from your segmentation. So when you have something like a small enhancing tumor prediction like the one here, which could or could not be a false positive, removing that actually can give you a bump in the metrics. So that's also something we've been doing here. And then using these kinds of tricks to specifically optimize for the validation scheme that's being used by the challenge is one thing, but the other thing is to think about the ranking. And here in breadths especially, people really like to report mean dice and Hausdorff distances in their papers. And this is not what the challenge uses to rank teams against each other, because it's a ranked and aggregate approach. And in this publication here in this year, we really were focusing a lot on recreating this ranking and ranking our internal models against each other this way. And I'm not entirely sure if it made a difference or not, because in the end, those two targets were kind of similar, but I think it's important to think about these things and think about it moving forward and always keeping that in mind. About validation strategy, often competitions provide an official validation set. That is a fantastic idea to get a standing of where you are versus other teams. But I would be really careful with optimizing my models solely on the validation set. That is because the validation set is often smaller than your training set. And because it is smaller, you could say statistical power is, in my opinion, not as reliable as when you use the training set. So what I really like to do is just run cross-validation on my training set, 5-fold cross-validation, use all the training cases I have, which, for example, in some competitions, there may be 200 training cases and 50 validation cases. So for me, it makes much more sense to trust those 200 cases and then occasionally take the additional 50 to verify I've been going in the right direction. And then if there's, for example, a toss-up between the two, so one model is better on the validation set, the other one is better on the training set, then I really have a preference towards the training set because it's larger. And I think this has often prevented situations like the one I'm depicting here on the right, where you're like really good on the validation leaderboard, but you've secretly just been overfitting, and then on the test set, things break apart. What I'm saying here, of course, only applies to competitions where there is like a, you could say, random split between training and validation cases. For competitions where you have, for example, an explicit domain shift or something like that, you would, of course, want to use the validation set instead. But like for the general use case, this is how I like to operate. Researching what kind of models you're using. I think this could be considered controversial, but in my experience, fancy models don't translate into fancy performance, at least not initially. So really focusing on basic methods and instead make the execution as good as possible brings you way further than like overcomplicating things from the start. So when you do research for competitions, don't get carried away by bells and whistles, and instead research competitions, not papers. Like look at other similar competitions, what has been winning those over the last years, what were like the patterns that emerged in this research, what is over and over again in the top of the charts, and this is probably then what you should start with. And only once you have this set up and completed and you don't know what to do anymore, then you can of course start looking into bells and whistles and make things fancy. But to me at least, like for example, NN unit in the medical segmentation decathlon, that was supposed to be our baseline, but nobody was able to beat it. So our baseline became the actual method. So think small at the start. You can always make it bigger and more complex. Another publication I'd like to highlight here is really this revisiting ResNets one. I like that a lot because the authors here essentially showed how this old ResNet architecture from 2015 could be is still state of the art if you do it correctly. And this is kind of the message that, or the things that in my experience, like how things are in my experience as well when it comes to segmentation challenges. Also to maybe in the interest of time, I will skip this slide because otherwise I might be over time, but I just wanted to show here an analysis of the Kids 2019 leaderboard, where we are essentially seeing that using something like a UNet architecture is really important to be good, but then what you're doing exactly, like if you have residual UNet, standard UNet, use dilated convolutions, attentions, cascaded approaches, etc., really doesn't matter. And to drive this point home, I also just wanted to note that that NNUNet then out of the box without anything was able to beat the winning solution of this competition then again 1 year later. So standard UNet was here the way to go, and it's really cool to see that even in such a competitive setting that can win. Which brings me to baselines. Before you start anything, build something simple, or even better, use something that you can just download and apply to your data set. Because if you're not grounding your results in the sense that you get some external validation that you're going in the right direction, and you're not, I don't know, that you're not losing yourself in some local minima somewhere and are like far from the global optimum, then baselines can really help you do that. And in my opinion, and I'm of course not entirely subjective in this matter, for segmentation tasks, NNUNet really is the way to go. So there's nothing preventing you from downloading NNUNet, applying it to a new challenge data set, and just see where it goes. I mean, this I mentioned at the start that we are currently participating in the AMOS challenge, and until like 2 or 3 weeks ago, and the challenge had been running for a while, a colleague of mine had submitted the standard NNUNet to the leaderboard, and it was like ranked 6th out of over 60 submissions. So I'm really asking myself, what have the other 50 people been doing? Because that's really like the download and apply thing where you don't have to switch your brain on it all. So do this, and then what I personally like a lot about NNUNet is that you can then also just use it for method development. And a really cool paper by Junma showed that in 2020 at MICCAI, 9 out of 10 challenge winners actually used NNUNet and built upon NNUNet to generate their challenge winning submissions. So sometimes you can even use the baselines as a starting point for task-specific optimization. I think this shouldn't surprise anybody. Engineering wins challenges, and sometimes you gotta descend from the ivory tower of science. So it doesn't have to be pretty. It doesn't have to be nice. It doesn't have to be mathematically sound. It really all doesn't matter. All it matters is it's better on the data than whatever you've been using previously. So use whatever tools you can, use whatever tools your GPU setup allows, like ensemble as many models as you can, use regularization. There's no such thing as overfitting the metrics. This is kind of the whole point of challenges. So overfit as much to the validation setup as you want. Yeah, look what things work on the data set and just do it. And that's the nice part, to me at least, for challenges, is you get rewarded for doing something well, not for doing something novel. So there's no reason to try and do something novel if you don't have to. So do what works, and if something novel works, hey, that's perfect, but it doesn't have to be. And this lifts kind of a nice constraint that we are typically, in my opinion, suffering from in academia. So it's just cool to see that challenges offer a refuge for this kind of work. When you're working with the data set, be one with the data. And I'm saying that here explicitly and very loudly because people like to treat their data as a black box. And I'm also seeing that with people from my team, with people from our department. They implement some validation setup and then just grind this one score that the validation setup puts out. And that's really dangerous because you don't understand the problems that your method may be having, right? So you have to, my concept is really visually inspect everything. So from data exploration to failure analysis, look at everything, look at the failures, try to understand why they happen. And just to give an example here, on the AC/DC challenge, for a long time, we weren't understanding why our 3D model was performing poorer than the 2D model. And in the end, after looking at the images for a while, we noticed that we had a big problem with interpolation because the spacing between slices is very large, and we were essentially picking the wrong target spacing for resampling, which caused a lot of interpolation artifacts. And only looking in the data could tell us that this was the problem. And I would argue that this is also what brought the challenge over the finish line for us. So it's really important to understand the failures and try to like purpose-build solutions to fix your failures. And finally, hyperparameter tuning, the dreaded one. Most people like to do it manually, including myself. I think only very few people in the world have enough resources to automate this process. But it's something that's fundamental, right? There's no discussion about it. And one thing I feel like it's sometimes underappreciated is image preprocessing, especially when it comes to resampling strategies, and also the target image spacing that you're using. So when you're thinking about CT scans with a size of, say, 512 pixels cubic or something like that, you will never fit that in one patch in the GPU. There's just not enough GPU memory for that. So given your GPU memory constraints and the patch sizes we can process, the image spacing essentially controls how much of a patient or how much of a training case you're seeing in a patch at one time. And this is really important because some things you can segment just based on the texture. So it doesn't matter if the image is huge and you're only seeing a small part of it at a time. But if you have structures where you really need the shape of the entire structure, then zooming out by increasing the spacing and reducing the image size really gives wonders. And the kind of balancing resolution with spatial awareness is critical hyperparameter, in my opinion, that should be optimized in every competition. On the other hand, intensity normalization is something people have been really obsessive about, and in my opinion, not in my opinion, in my experience, it really isn't super critical as long as you're consistent and reasonable. So even for CT image, just z-score that and it's going to work just fine. So I mean, you can of course try some things, but it's not the first thing I would be looking at. Same with other stuff like bias field correction, which used to be super popular in MRI images. If your data set is large enough and you use data augmentation, then you really don't need that. And I would argue that you should never include pre-processing steps for which you couldn't objectively show a benefit in your model's performance, because you're just including new error sources into the whole pipeline. So don't include anything just because people do it, but validate if it makes sense. And finally, I have some maybe controversial thing, and that is that I never seed my experiments. I hate seeding. And the reason is that if you do seeding and you have an internal leaderboard, what you're essentially doing is overfitting to your random seed, and don't do that. You want the noisiness that comes from different seeds. You want the model to be noisy so that you can understand the noise in the data, and so that you can essentially do your own noisy gradient descent along your hyperparameter space. But I never use seeding. I understand why you do it for publications, but I would never do it for competitions. Yeah, so let's wrap things up. In my opinion, not every challenge is worth fighting for. Look what you want to compete in, understand the challenge, build a proper validation environment, make sure you're optimizing the right metrics. When you're researching, focus on competitions first and only then fancy stuff later. Start simple, use ready-to-use baselines, visually inspect everything from raw data to metadata distributions like spacing, plot them, I don't know, look at your failure cases. And finally, engineering and hyperparameter tuning may be really boring, especially if you're an academic, but that's what will grant you the win in the end. So that's it from my side. Thanks so much for joining in, and I'm really looking forward to the discussion.
Thanks a lot, Fabian. I think this was really helpful for the audience. I'm also continuously learning from you. Maybe 2 comments from my side, because yeah, I'm basically Fabian's colleague, and I think the audience should know. So you did see how Fabian basically has several tricks to leverage challenge design, for example, leveraging the metrics, etc. But there's one thing he was always very concerned about. And I remember when the team participated in the decathlon, multiple test submissions were actually allowed. And Fabian said, I'm not going to submit more than 1 time. I'm just going to do this 1 submit, and I don't care where I stand, but this is where I stand. I'm never going to overfit to the test set. And that's what he did. And he won the challenge. And I think that's actually pretty impressive. And the second comment I just wanted to pitch, because also some of you are aware that we did an analysis, or we are in the process of doing an analysis. Why is the winner the best? You know this because some of you participated actually in our questionnaire. So what we did last year in MICCAI was to ask all the challenge participants a little bit about their strategy, so we can match the ranks and the challenge strategy. And I just want to give some teaser in support of what Fabian just mentioned, which is that those, basically, if you look at winning teams versus not so well-ranked teams, the winning teams spend much, much more time in failure and data analysis. So this is a very clear takeaway that we have. So yeah, many thanks, Fabian. And let's move on to the next speaker and then finally to the questions by the audience.
Okay, great. Yeah, thank you. Thanks, Fabian, again for sharing the tips, insights. Excellent. I hope actually the audience can learn how to better win challenge, but the challenges also will be more challenging than ever. Okay, all right. So logistic issue. So we'll have a panel discussion as mentioned by Lena after the second talk. So Annika will moderate the discussion. So everyone, please get your questions ready. We have limited time to answer the questions. So either type in the Q&A or raise your hand at the end of the talk. So our second speaker of the day is Dr. James Howard, who is the academic clinical lecturer and a cardiac imaging fellow at Imperial College London. So he received his PhD in convolutional neural networks. James is a rare academic cardiologist who is very good at developing AI models. He has published numerous research papers using AI to interpret X-ray, cardiac ultrasound, ECG, MRI, and cardiac pressure waveforms. So he has entered several Kaggle competitions, including the deepfake detection challenge, where he won a gold medal and $40,000 prize against other 2,200 teams. So let's welcome our speaker. James, you're on mute.
Hi, hopefully you can hear me now. I lost the mute button when I went full screen. Is that working?
Yes, perfect.
Great, okay. Yeah, so thank you very much for inviting me, everyone. It's a real honor to be speaking here, and I'm going to speak a bit about my experience as a doctor with these competitions and how I tackle them. So just a little bit about myself. So my day job is I'm actually a cardiologist and I work in a hospital in West London called Hammersmith, but I'm also employed by my university, Imperial College London, where I do research in cardiac MRI scanning. But prior to this, I did a PhD in AI, in convolutional neural networks, and I worked across a variety of fields. So I wrote an app that examines chest x-rays to identify what type of pacemaker a patient had. I wrote an AI that analyzes cardiac pressure waveforms. I wrote an AI that assists in the implantation of pacemaker wires. I wrote a system that examines orthopedic implants. And more recently, I've written a segmentation system that actually runs on the MRI scanners at our hospital that segments out the cardiac chambers and provides you a result during the scan of estimated heart volumes. Now, the thing is, none of these solutions are actually particularly groundbreaking technically, but they're all inspired by real world problems and they're all very different data sets. And what they did give me was a wide appreciation of ways to tackle AI projects, because I'd done classification and segmentation tasks of 1, 2, and 3-dimensional data. And I believe it's that sort of broad skill base that has helped me to have some success in these AI competitions. And for me, this has mainly been via Google's Kaggle platform. And today, I just want to speak to you about a few insights I've gained over this time that I think can make a big difference in these competitions. So the first thing, and we've heard about this already from Fabian, is think about the data, okay? And I know that sounds really vague and unhelpful, but it's actually really important. And another way of thinking about this is, what dirty little hack could I use that other people haven't that might make my and the neural network's life a little bit easier? So my first challenge at Kaggle was this deepfake detection challenge. And this was a challenge where Facebook and Microsoft put up $1 million in prize money to stimulate people to develop models to identify deepfakes. And deepfakes are images or videos where the original video has been altered to have someone else's face, commonly associated with fake news. And they're interesting. And I've shown you two here. They're paused at the moment. And actually, whilst they're paused, they don't look that different. And you can believe that they were real pictures. But if I click play, you can see there's all these funny artifacts because the frame to frame differences are not correct. So on the left one, the neural network's struggling to standardize the lighting between frames. And on the right, there's something very unsettling about how his facial features move around and something about his eyebrows. And this reminded me of my experience with medical ultrasound, because in medical ultrasound, often when the video is paused, it can be quite difficult to see the edge of the organ or structure you're looking at. But as soon as you press play and you get movement, your eye is drawn to it, and it's much easier for your brain to make out the border. And I've done quite a lot of work in classifying ultrasound videos, so I thought I'd give this challenge a go. So I downloaded the data set, and then I looked at one of these videos and my heart sank. They are absolutely huge. The data set was 470 gig zipped, and often you can see the face moves across the screen, and they might just be a very small section of the screen. And I thought, there is no way, like Fabian said, there is no way I can fit a video of this size at any decent resolution into any video classifier, any 3D neural network on the planet, even with the world's best GPUs. So everyone else realized this too. And what everyone was doing was they were identifying the faces like this, and then they're extracting these as a series of images, and they were training a network to classify them as simple images. But like I said, I knew all the good stuff was clearly in the video information, okay? And it wasn't obvious in a single image. So what I did in the first week of the competition was I wrote this function, and all it does is identify a face in each frame, and it tracks that face through space, and then it crops down the video as small as it can make it, so the entire face is cropped down to, and then it exports it as a very short MP4 file. And I exported 200,000 of these MP4 files over the space of about 24 hours through an automated script and a face detector. And I then trained just a simple off-the-shelf 3D convolutional neural network, Inception 3D of this, and went straight into 4th place. 3 weeks into a 3-month competition. And this was really exciting because it was my first competition, and the Facebook team were in 6th place. But the problem was there was 3 months left. So over the next 3 months, I teamed up with another chap called Ian Pan, who's a grandmaster at Kaggle, and he developed a 2-dimensional network, which we ensembled with, and I trained 7 different 3D networks, and we ensembled them all together. And like I said, we started off in 4th place, but as the competition went on and on and on over the months, I fell further and further down, dropped out of the money position, dropped out of the gold medal positions, and ended up in silver territory. However, as you probably know, when these competitions start, the organizer, so Kaggle, will release a big training data set. But there's another data set called the testing data set, and they keep this safe, and you never see that. And the idea is that you then train your model on the training data set, and you write some code, some inference code that will read in the data and produce the predictions, and you send that to Kaggle. Now, actually, the testing data set is then split into 2. It's split into a public testing data set and a private testing data set. And as soon as you send them your code, it will process the public testing data set, and it will update the leaderboard. However, as soon as the competition ends, the public test set is irrelevant. The entire final leaderboard is based on the private test set. And so people's positions on the leaderboard, as soon as the moment the competition ends, all get reshuffled. And this is a, in Kaggle sort of terminology, this is called shake-up. And after shake-up, it was very kind to us, and we shot that up to 5th place and got our gold medal and our prize money. So that was really exciting. And this was my first competition, but I learned a lot of very useful lessons from this. The first thing is trust in your methods. And not the public leaderboard, partly because you won't win competitions doing the same thing as everyone else. So if you've thought of a novel method of doing it, it's worth a go. Also, if your method is logical, like I thought the video thing was, based on some insights into the data, I think shake-up is far more likely to be kind to you. The second thing, and possibly even more influential, was, for me, do not join at the competition launch. The stress I had of starting up in 4th place and then seeing team after team overtaking me over the next 3 months was so disheartening. And so I think if you can join later on in the process, you'll be saved that, and you could also sort of stand on the shoulders of giants and fork their code bases and see what everyone else is doing before you turn up. Anyway, just to sort of hammer home this tip again, I've got a second example. So the next competition I took part in was this one, being run by Berkeley in California. And they wanted a neural network or any form of AI that would analyze signals coming back to their telescopes and help identify if the signals they were getting back were generally from outer space, maybe aliens, but maybe like a star exploding or something like that, or noise, because, for example, someone's using the microwave in the coffee room and the telescope is picking it up. So they released 100,000 spectrograms, which look like this. They're actually grayscale, but they're colored for this. And they're made up of 6 measurements, formed immediately one after the other. And 3 of these measurements are when the telescope is aiming at the bit of the sky that they are interested in. And then what they do is, interleaved within these 3 measurements, they have 3 other measurements where they look at a random other bit of the sky. And you can see there are some signals, like this green line, which is only present when they're aiming at the correct bit of the sky. But then there are other signals, like this red line, where regardless of where they're aiming, they see it. And that must be noise. It can't be coming from that bit of the sky. It must be coming from somewhere else. So the aim of this challenge was to take these spectrograms and decide if they contained a genuine signal or some noise or artifact. And I joined this competition with only about 3 weeks until it finished, rather than the 3 months previously. But I immediately knew how I was going to tackle it. So as you all know, every image on a computer is actually stored usually as 3 images: a red image, a green image, and a blue image. And then they're combined to give our color image. So what I did was I took the spectrogram and I turned it into the red image of a color channel using this simple lines of code above. And then I would take a green image where it has bands where the telescope was looking at the area of interest, and a blue image where it was looking at the control location. And then you combine them all into a single image. And now the brightness of this image corresponds to the signal you're getting back. That's your spectrogram. But the color responds to the location. And what this means now is I can now randomly crop or distort or rotate this image, and the network will still know when it's looking at which bits of the night sky, which is incredibly important. And you couldn't do this without doing this sort of channel hack. And this seems so obvious to me, but it led to me getting 6th place. And to be honest, I'm maybe even slightly prouder of this one than the deepfake one, because like I said, I only took part in the last 3 weeks and submitted 13 versions of my notebook, as opposed to the 100 or so that everyone else above me submitted. So in this one, I sort of learned also the importance of a good workflow, and you can succeed in a relatively short interval as long as you can get things working efficiently and autonomously. And in fact, I was on my bachelor party or my stag do before my wedding when my best model was training, because I'd left a queue of different experiments to run on my computer. And I came home from this and I was able to rapidly narrow down the number of models I was going to run inference on and send to Kaggle. And to do this, I personally use a system called weights and biases, which I really love for tracking experiments and performing hyperparameter sweeps. But any system that allows you to systematically examine your experiments is so, so useful. So that's the first tip, thinking about the data. The second tip, and actually I was so pleased because Fabian touched on this as well. It sounds like we'd conferred, but we hadn't, I promise, is do not obsess over model architectures. So this is one of the most famous figures from AI papers in the last few years. It's from the EfficientNet paper back in 2020. And what they show here is, with the red line, how well the different sizes of EfficientNets work at classifying ImageNet. And what's remarkable about this graph is how much they had improved upon the state-of-the-art models just a couple of years earlier. So here we see ResNet 34, and it has 73% accuracy on ImageNet. And then if we look at the corresponding EfficientNet with the same number of parameters, same number of neurons, we get 83% accuracy. So they've reduced errors by 1/3 for the same size network, which is huge. However, there is more to this than meets the eye. This is actually a paper that Fabian had in his references in one of his slides, I noticed. And it may be my favorite AI paper. And it came out last March. And that includes this figure, which is similar to the previous one in the EfficientNet paper. And here we see trusty old ResNet in green. And then what the authors then did was they made some simple changes to ResNet, and they showed not only could they achieve EfficientNet performance, they could actually go past it. And the changes they made to the network were not new discoveries. They've been proposed back in 2018. They were things like adding squeeze excitation layers and adding and changing the way the residual connections worked. But they noticed massive gains, and now their ResNet was better than EfficientNet. And this seems too good to be true. And in fact, as the authors admitted, it is too good to be true because they included this amazing table. So what this table shows is if you just get your ResNet off the shelf, this is ResNet 200, and it has about 79% accuracy. But if you add in a cosine learning rate decay, and you increase your training epochs, and you add in exponential moving averages, and you add in label smoothing, and you use stochastic depth, and you add in rand augments or different augmentation strategy, and you add a dropout layer on your fully connected layer, and you decrease your weight decay, you are now 82% accurate on ImageNet. You are now as good as EfficientNet, and you have not changed the network yet. If you then add in those squeeze and excitation layers and this slightly different residual pathway, you hit 83.4. You are now above EfficientNet, but the vast majority of these benefits are before you make any difference to your network. And for that reason, I firmly believe that it is your training loop that matters more than your model. And I think actually you could do a lot worse if you're trying to figure out your training loop than downloading the TIM library and having a look at how that recommends you train your state-of-the-art models. It has example parameters for all the models on the leaderboard, and just see how they write their training loop. And if you want to fork that, then you're off to a winning start, I think. The third tip, and this is probably the most controversial, but I also strongly believe it is true, and again, Fabian also touched on this, is medal winners are made by their inference code. And in fact, I said to a friend the other day, I think I would rather finish a competition with an average model, an average neural network, but the best inference notebook, than finishing with the best model and an average inference notebook. I think the inference notebook is the most important thing. And you're saying, oh, come on, it's very easy for you to say, do you really expect us to believe that? Well, I've actually put my money where my mouth is. And last week I signed up for this competition. And it's got 2 months left. So I've broken my golden rule of joining a competition in the last few weeks. I've joined it with 2.5 months left. So I'll be lying in bed at night, refreshing the leaderboard and not getting any sleep. But anyway, in this competition, what you do is you get microscope slides, such as this one, and your aim is to segment out what are called functional tissue units, such as these bits in red, and then you submit these segmentations to Kaggle. And I went on the Kaggle forums, and I noticed that position 24 down to position 113 all had exactly the same score. And that's because this person called the Devastator has shared an excellent notebook with a UNet with a red snaked backbone in it. And you can open their notebook and you can click fork and edit, and you can run it and you can submit and you'll have the same score as him. And that's what 100 people have done. But the reason why this is possible is he has also shared his models, his pre-trained models. He's shown 4 of them. And so what I did, I set myself this task. I said, I need to show that inference is what matters. So using only these neural networks, how much performance can I squeeze out? And I started looking through the challenge, and what I realized is this is quite an interesting challenge. Here, inference in this challenge, even once you train your neural networks, is not straightforward for several reasons. The first thing is the source images are big, okay? They can be up to 20 megapixels in size. They are way too large to fit into a GPU. Maybe you could fit them into 80 gigabyte A100 with mixed precision, I don't know, but I think even that would be a push. But you definitely don't have that at Kaggle. So most people split their image into smaller tiles, and often they'll also downsample them as well. But there's loads of ways you can do that. The second thing is there are different body parts of different difficulties. So I've been reading through the forums, and it seems that people are struggling to get their networks to segment lung images, whereas gut images are quite difficult. And at test time, you actually can read the metadata and see which one you're looking at. So maybe the analysis should account for this. And then the third thing is the testing data set is very different. It's a little bit peculiar, but it's intentional, very different from the training data set. So these are some examples that I've taken to the forums from a user called MICCAI SIG. And what he shows is, this is an image on the left from the training data set. And these are similar images on the right. And you can see the training data set tends to be more zoomed in. It uses different stains, so the colors are different. And also there's different tissue thickness. So there's different amount of light coming through. And all of these make your inference pipeline a little bit more tricky. So I set myself the challenge, and I took the same neural networks as the 100 people who previously submitted it. And I just rewrote the pipeline based on what I thought would be helpful. And I went straight into 13th place. So they were all in the 20th place to 100th. And to put it into context, this is halving the gap between the notebook I forked and 3rd place. So I'm halfway closer to the money using exactly the same neural networks as everyone else. And I suspect I can make some other tweaks. Unfortunately, I can't talk about it now because I'll get sacked. I'll get disqualified from the competition. But I'm sure if you spent there long enough, you could do it yourself. So, so in summary, what I wanted to say is the 3 things I think are most important is, first, think about your data. I think intelligent pre-processing, so for example, in the deepfake challenge, using videos, not images, in the SETI challenge, adding color channels to allow the network to orientate itself, they were probably the things that helped me get my medals. I truly believe that network architectures really are not that important, and actually how you train them is more important. But I think the most important code you will ever write in a competition is your inference notebook. And for some reason, I don't seem to have finished this sentence, but that is the most important code you will write during a competition. Thank you.
Yeah, thank you very much, James. Now we hand it over to Annika to moderate the panel discussion. It's very exciting to hear all those stories and tips and tricks.
Yeah, thanks also from my side. This was really, really interesting to get those insights and also to see the synergies between the 2 talks. So it would be really great if you would like to stay for a few minutes so that we can discuss the questions, drop them in the Q&A, raise your hand, and we already have 2 questions and I will read them out. So the first one goes to Fabian. So thank you for the inspiring talk, Fabian. You mentioned the interpolation artifact occurrences due to the incorrect resampling spacing during the SGC challenge. Did you encounter the problem for the segmentation task or the classification task of the challenge? And also, have you done anything apart from using a 2D model for this particular objective?
So the interpolation problem, we only had that for the 3D model. And of course, that was the segmentation task. And so in the end, in this competition, the ensemble between the 2D and 3D model was what was performing best after we did this fix. So essentially, there were in this data set, there were 2, I don't know if it was image sources, but a lot of images had a spacing of 10 in the out of plane axis, and a couple had spacings of 6, 7.5, and 5. And just because the 10 was the majority, that was what we were resampling to, but then resampling back from the model, which predicted at the spacing of 10 to these other spacing, just had too many interpolation artifacts, and this was noticeable, and this really dropped our scores. And fixing that by just switching to a target spacing of 5 instead of 10 for this axis, that fixed all the problems.
Thank you. We have another question for you. Could you give us an example of how visually inspecting the model's failure can be used to improve the model?
It's hard to come up with an example right now. The thing, what I really like to do is when I run the evaluation, sort my cross-validation cases from worst to best, and just look through them and identify the errors, see where they're coming from. And very often that this actually led to me finding mistakes in the annotations of the data set, which then caused me to reach out to the data set providers and complaining about that. And if the challenge was good, people actually fixed that. That was so that was really helping out a lot. Also the other participants. But sometimes when things couldn't get fixed, and I was actually convinced that my model was correct and the prediction wasn't, I actually replaced the ground truth label with my prediction So that's where it really helps to see, for example, when mistakes are in the annotations, you can get away with taking, for example, predictions of your model instead, if that's allowed by the competition rules, that is, of course.
All right, next question for you. You won your first competition. Does it mean that a good method is much more important than years of experience? So as a beginner, that would be reassuring.
Honestly, it's been a while. I don't think you need a lot of experience to do it. I think just go for it. It's important to put your energy in the right places and don't waste time on things that are not going anywhere. And I think James and myself today gave you some hints on what it's important to focus on. And then I can only encourage you to start with your first competition, gather experience, and see where things are going.
So if you do not use a constant seed point in your experiments, as you said, so e.g. fivefold cross-validation, how do you compare the experimental results to select the best type of parameters?
I just picked the best one or the best ones. So I'm thinking of the model optimization process as just a noisy, you could say, gradient descent. So I'm just training a bunch of models with different variations, and in the end, I'm picking the best one. But it's never a one-shot process, right? You're not just testing everything, then picking the best one, and that's it, right? So you're doing something, you're picking the best one. From this point, you're again doing something, picking the best one. And because you have this sequential process of optimizing your model, I think you're essentially canceling out that noise over time. And I think this is kind of important, at least in my experience.
So to both of you, how much time do you invest in these challenges? Like how absolute amount of hours that you spend?
Yeah, good question. I think it sort of depends. I think you can spend as much or as little as you want. I personally, what I tend to do is when I join them, I probably spend most of a couple of days working on it. But then once you have a working pipeline, everything else is very incremental. And I tend to either just leave experiments running or wait until I've had a little bit of inspiration. So I probably won't do anything on that HubMat challenge I just joined now for a week or so until I can think of something clever to do. I could keep training slightly different networks, but the incremental benefits are often quite slow. And the small things you see just from training and training and training are often just random noise, to be honest.
Yeah, so for me, it's kind of difficult because I actually am supposed to do other things in my work time as well. So I'm more like looking where I find the time still to do stuff. So for the Amos challenge, for example, you could say it's been one work day of actual working, but that was of course distributed over a couple of weeks. But what I noticed is that the time I spent for each competition is kind of decreasing. So the most was probably in 2017 with Bratz and AC/DC, but especially because I've been, you could call it grinding segmentation challenges. It's been more of a rinse and repeat process lately. So you can get away with less time per challenge.
Fabian, could you mentioned the rank and aggregation. What does rank mean? Rank different designed models or what?
So this is essentially two different strategies for how you can compare different algorithms. So aggregate then rank means that, so if you have, for example, a segmentation problem and you're evaluating with the dice score and you have 100 test cases, you take the dice score of each of the 100 test cases, you average that, and then you rank people based on the average dice score that they are getting. And rank then aggregate means that you take each of the 100 cases individually and on each of the cases rank people against each other. So you get a rank per case and then you average those 100 ranks. And because you're doing it like one thing is the other way around than the other, this can have implications for how the final ranking performs. So for example, if you're performing poorly in a rank then aggregate scheme, it doesn't really matter how poor you perform because your rank cannot get any lower. So it has a different emphasis on different like on your distribution of scores, I would say.
A question to both of you. I was wondering if you know whether the winning strategies that you have described today are also in line what other top ranking participants do, for example, focusing on training rather than fancy models.
I would say yes. You often, to be honest, it's very rare in my experience you find a competition has been won by the biggest network. There are a couple of networks that always pop up. Squeeze excitation ResNext as a background for UNet. UNet always does very well. A lot of people use that, and then a lot of people use efficient nets. Efficient nets are really nice because you can start with a small network and slowly build it up and see at what point you seem to get decreasing returns. But actually people tend to not use very many other networks. And I don't think that's because these ones are so much better. I think it's because there's relatively little to learn. What we have to remember is all the papers that publish the results for this on ImageNet, which is 1,000 classes. And so I think these networks are always much wider than they need to be in terms of number of features. And so I just don't think I think they always tend to be a bit overkill, to be honest.
I would totally second the statement. I'm often asked, like, what do you think about network architectures? And you've been promoting the UNet for 5 years now. What's the next step? And I really think that for the small data sets, the exact architecture you're using really doesn't matter too much. I mean, in some data sets, you see difference between, say, a residual encoder and a standard UNet convolutional encoder. But to be honest, the differences are minimal here. So there's nothing, it's nothing similar like on ImageNet. And what we also always need to keep in mind is that when people are reporting ImageNet scores like over 80% accuracy, etc., I'm always wondering how much test set optimization actually went into that, because the people have been grinding this challenge way too much. And it's really something where I'm skeptical on how much of the results there will translate into results on other data sets.
So what tools are you using for hyperparameter tuning?
So I used to do it manually, actually, like Fabian, but recently I have fallen in love with weights and biases sweeps. They can be a little bit painful in terms of getting it working with distributed data parallel if you have multi-GPU setups, but it is actually possible. And if you're into those problems, you're welcome to email me. But I really love it because I really love their web interface, because I can check it from my phone when I'm at work during the day and things like that.
I'm really old school in that regard. I just run my experiments. I plan them manually and I evaluate them manually using scripts to collect all the results.
Maybe in the interest of time, we close the webinar officially, but then in case James or Fabian have time to answer the remaining 3 or 4 questions, it would be great if you stay online. But then at least we keep our time somehow. I will keep it very, very short. I really want to thank you guys for coming. I think that's my impression. It was really a great session for the audience. And to the audience, stay tuned. We will have new webinars coming up. We will keep you informed online, basically. And with this, yeah, thanks a lot and have a good rest of the day. And again, you can stay, we will stop recording now and you can stay online for the remaining questions.